In this video, we will finish up our discussion of circular motion and summarize the equations that are pertinent. Continuing from the last video, we were looking at rotating vectors, moving around the circle, and for both position and velocity vectors. And now I want to find the speed. How fast is the object moving? You only know the radius of the circle and the period of revolution. So speed, by definition, is displacement over time. Well, so you can kind of think of what is r doing as it goes all the way around the circle. The magnitude of the position velocity is changing. So there's a delta r over t, but that's really just 2 pi r over t. It's the circumference divided by, I went from small t to big T. Big T corresponds to period, which is the time. You make one complete cycle, vibration, oscillation, right, sequence. So that's what that is. Go around the circle once, that's the period, the time. 2 pi r is the distance. So that's pretty straightforward. But now, we looked at the velocity vectors, and by analogy, they were doing the same thing the position vectors were doing. So the velocity vectors hooked off perpendicular here, rotating all the way around. They also went through a similar quantity of change in their value. So that's the premise where I'm moving forward with here. So how can we find the magnitude of the acceleration if you know only the speed and the period instead of r and the period? And we just saw that the change in velocity is perpendicular to the velocity. All right, so that's true everywhere along here. And then we put all the tails at the center of a circle, and we saw the velocity vectors really looking the same as the position vectors, rotating around the circle. So here by analogy is what it is. A is delta v over t, just like v is delta r over t. And the delta v, how much magnitude of change it's gone through, is likewise, by analogy to 2 pi r, it's 2 pi v. V changes by a factor of 2 pi as it goes around the circle. All right, so that's how we can think of it. And we just have our first equation for the acceleration of an object in circular motion. Here again is the radii and the velocities at 4 different locations, okay? And now we know that the delta v is pointing inward, because the delta v really at this point for v1, remember, v2, if we make delta t really small, will be right next to it, and the delta v then connects the tips across, and it will be directly perpendicular, delta v. But delta v, how does that relate to acceleration? I think you know. Acceleration is delta v over t. They're both vector quantities. The t is a scalar. That means that that's the direction of acceleration as well. Acceleration is always in the direction of the change in velocity. So there's our acceleration vector. And likewise, we could draw the acceleration at different locations. It's always doing the same thing. And what I mean by doing the same thing is, if this is uniform speed, the size is the same, and it's pointing relative to v. Okay, what's this doing relative to the motion? Well, it's perpendicular. And there's more that can be said about that in a moment. What's the direction of a relative to r? What is a doing compared to the radius vector? Well, you could say they're collinear. Don't say they're parallel, because they're going in opposite directions, or anti-parallel. There we go, anti-parallel. And now since r points away from the center of the circle, what is the direction that a points? A points in the opposite direction, or toward the center of the circle, and that is very key, very important. In fact, it has a special name. A quantity that's pointed toward the center of the circle, and in particular, this kind of acceleration is called centripetal acceleration. And that is to be distinguished from centrifugal acceleration. You've heard of centrifugal force. We're going to be talking about centripetal force toward the center. Centrifugal means away from the center. Most people are more familiar with that term. We will strongly and clearly distinguish it from centripetal that we just described. We will now present all the equations of motion for circular motion that we need. First of all, we've seen that v is equal to 2 pi r over t. If you know the radius, the period of rotation, there you go. Now the magnitude of acceleration for an object moving in a circle, if you know the speed and the time around the circle, is similar, 2 pi v over t. Very useful. We're now going to eliminate t in these two equations and solve for the acceleration as a function of v and r. So we'll solve for t here, stick that in for this. So here we go. T is 2 pi r over v. And now we have a is 2 pi v over t. And for t, we're going to put what we just solved, 2 pi r over v. So there it is. And even though it looks like almost everything divides out, it doesn't. But the 2 pi's do. And we get acceleration is v squared over r, a very, very useful form for the acceleration of an object in a circle, which we now know is centripetal, or toward the center type of acceleration. Now we're going to eliminate v in the two equations above and having a formula for acceleration with r and t. Well, this is v, and so we can really stick that in, this result in, for this, over in this acceleration. So I'm going to bring this down. A is 2 pi v over t, and stick in for v the solved formula for t, which is 2 pi r over t. If you solve this for t, we get 2 pi r, bring the v over, there we go. And then that's all divided by t. So what does this give us? It gives us 4 pi squared r over t squared. That's the final version, final equation for centripetal acceleration. So in summary, a sub c, centripetal acceleration, 2 pi v over t, which is equal to v squared over r, which is 4 pi squared r over t squared. That's a nice summary. You should commit those to memory. And so now, just to summarize the various vectors, here we have the radius vector, the velocity vector at that moment. At that moment, the change in velocity is pointing perpendicular to the velocity, and really we could put that over here. That's where it's happening. But over there instead, I'm going to put a sub c, because centripetal acceleration is in the direction of delta v. And if centripetal acceleration is in this direction, an acceleration is associated with or caused by a force, as we've learned, studying Newton's laws. So I'm now going to put F of c. And if I ask you how to say this, you would say, well, force, oh, and you know that that c now means centripetal. So this is centripetal force. And there is the finish of our quick summary of circular motion and the formulas you need to solve problems, which is for the most part just plug and chug with these equations.